Well, hello and welcome to Fluids. This is going to be the Fluids video for the energy principle. Now, the energy principle in fluids is uh, an adaptation of the conservation of energy that you may have learned in the first law or in a physics class. So real quick, here's what it would have looked like in the first law. Potential energy at 1 plus kinetic energy at 1 plus internal energy at 1 plus any work on minus any work by plus potential energy at 2, my bad, plus any Q in minus any Q out equals, there we go, potential energy at 2 plus the kinetic energy at 2 plus the internal energy at 2. The units for this equation would be joules, foot-pounds. Now, as we modify this, we end up with the energy principle for fluids. In the energy principle for fluids, you'll see the similarities. But the height at point 1 plus the velocity at point 1 squared over 2g plus the pressure at point 1 divided by density plus any head added by a pump minus any head taken out by a turbine minus any head loss equals the height at point 2 plus the velocity squared at point 2 over 2g plus the pressure at point 2 over density. Now, let's look. Well, the potential energy, I think we can see that. It's there. It's there. Now notice we've divided by mg here. Kinetic energy. There. There. Internal energy is actually sitting in here where it's U2 minus U1. U2 minus U1. So there's the internal energy. And the work, remember now if you've had thermo, there are two kinds of work. There's shaft work, so this is shaft work on, and then there's flow work. And the flow work is sitting here in the pressure over density term. Heat transfer is neglected in the energy principle, so it's gone. And then this would be work by. So there are the connections to energy. And basically, like I said, all we did was we took the equations, whatever they were, mgz, 1/2 mv squared, all the way along, and divided by mg. And so you can see how it happened in these terms. It happens in all terms. Well, let's think of this in terms of the English system. If the units for mgz were foot-pounds, and we divide it by the units for mg, what is mg? Well, that's weight, pounds. We get an answer in terms of feet. And in fact, the units for the energy principle in fluids are a unit of distance, a unit of meters, a unit of feet, a unit of inches. So there we go. There's the energy principle. Let's talk about how it might be applied in an example. So just say, for example, that we had a tank of water at one height, and we've got a tank of water at another height. And between that tank, we've got a device. Between the two tanks, we have a device. And we'll let our device be either a pump or a turbine. You can see that if we were letting the water flow from top to bottom, we could have a turbine here and get some energy out. But if we wanted the water to flow from bottom to top, it would require the use of a pump. So let's go ahead and go from top to bottom. As with the first law, as with the conservation of energy, the energy principle, and oh, by the way, remember, these are three of the same thing, three ways of saying the same thing. You have to choose your endpoints. Well, I'm going to choose my endpoint to be here, at the top of the tank, and here. And I'm going to write the conservation of energy, or the energy principle, from point 1 to point 2. So, Z1 plus V1 squared over 2G plus P1 over, I've been saying rho, but I do believe that's supposed to be gamma. P1 over gamma. My bad. We got to change this to gamma. Change that to gamma. And I suppose we need to know what gamma is. Gamma is specific weight. Specific weight. At the end of this video, I'll jump in and talk a little bit about gamma. She was a nice old lady. Plus any head added by a pump, minus any head taken away by a turbine, minus any head loss, equals the height at point 2, plus the velocity at point 2 squared over 2g, plus the pressure at point 2 over gamma. And one of the reasons the conservation of energy principle is always one of my favorite engineering principles is simply because you can always cancel a whole bunch of stuff out, and it makes it pretty easy. Well, as you recall from the previous experiences with conservation of energy, we're the ones who get to say where the potential energy is 0. So let's choose the potential energy to be 0 down here at this point, and then the potential energy up there will just be the Z1. So there's our first cancellation. Z2 is 0. If I choose my points up here in these big tanks have very little velocity in them because they're so big, and there's a lot of velocity in the pipe, but very little there. So we use what's called the big tank approximation, which says that the velocity at point 1 and point 2 is equal to 0. Another cancellation. Woohoo! The pressure at point 1 is atmospheric pressure. What's the pressure at point 2? Atmospheric. So whatever atmospheric pressure is, it cancels because it's on both sides of the equation. Now, as we said here, we're going to have a turbine. So if this is a turbine, there is no pump. And what we're left with, I'll write it up here in another color, is that the turbine head, rearranging, is equal to the height minus the head loss. So the amount of energy available to us in this turbine is equal to the potential energy of the water at its highest point minus the energy lost due to friction in the turbine. Very cool. And you can see that if this were a pump, the pump head would equal the height that we have to achieve plus the energy the pump would have to overcome due to friction. You can see that difference comes from the plus and minus on this side of the equation. So there's an example. Okay, I promised we'd talk about gamma. Well, gamma is a Greek letter, and it stands for specific weight. Specific weight is the weight per unit volume of a fluid. So if we were to take a cubic foot of water and put it on the scale, it would weigh 62.4 pounds force. So, specific weight of water is 62.4 pounds per foot cube. It is, and you want an equation for it, it's equal to density times gravity. And let's check to make sure that the units of that pressure over gamma that I had wrong are correct. Let's see. Pressure is pounds per square inch, and gamma is pounds per foot cubed. I would have to do a unit conversion here. 12 inches in a foot. Need to square everything. So we have 144 inches squared in a foot squared. Pounds cancel. Feet squared cancel down to feet. The units here would be feet. That's how I caught myself on that first run through the energy equation. So that term is in fact pressure divided by specific weight. All right, that's it for energy.